In this video, we're going to explore large linear systems using the matrix exponential. So the definition of a matrix exponential of an n by n constant matrix A is defined as E raised to the matrix A is multiplied by T, which is equivalent to the identity matrix of the n by n plus the matrix A multiplied by T, the matrix A squared multiplied by T squared over 2 factorial plus A cubed, T cubed over 3 factorial, etc. Now, this is where you're going to think about, oh, this must be the Taylor series. So we have to think about into calculus 2, at the end of calc 2. And at the time, it seemed really weird to learn about series, in particular the Taylor series and the Maclaurin series, because it just kind of seemed like it was in an odd place. And I said, well, this is where we have the mathematical maturity to understand it. And we didn't do anything with it. Well, now we're going to do something with it. For any square matrix A, any value of T, this infinite series of matrices can be shown to converge. So you might want to go look up what it means to converge if it's been a while since you've had Calc 2 or if you had it in Calc 3. Let's go through this example. So we want to find E raised to the AT, and it's just a computational, sort of computational. So the first thing I'm going to do is, I know what A is, right? So then I need to find A squared. So I'm going to go out and I'm going to either use my calculator to do A squared, or I'm going to do a matrix calculator online, and then basically A squared is A times A, which when I do that, I get 1, 4, 0, and 1. I'm going to find A cubed, because what I'm trying to do is I'm trying to figure out if there's a series that can be built. When I try to expand this out, I want to find a series so that I can find E to the A, and then all I have to do is just multiply by T, and then I can get what I need. So again, I'm going to go out either my calculator or online calculator, and I'm going to do the cubed, and I get 1601. And what I see is that there's a 1 in that 1, 1 position, there's a 0 in the 2, 1 position, a 1 in the 2, 2 position, and then this number, or this number, this seems to be looking like it's 2 multiplied by some n. So 2 multiplied by and 2 multiplied by some n. And the reason I'm saying some n is because if I notice that I have 2, my n would be 2. If I have 3, my n would be 3. So then if I say, well, A raised to the n the power, this would be equal to 1, 2 times that n power, 0, and 1. So now I have a way of expressing my A multiplication very simply. So then E raised to the A is going to be the summation of n equals 0 to infinity of T to the n over n factorial. Then it's going to be multiplied by 1, 2n, 0, and 1. And that comes from here. Now you're thinking, okay, I get the n factorial. That's cool. I get that. Where is this T to the n coming from? Because I'm not seeing that. Well, it's coming from up here. So I have A times T, A squared times T squared over 2 squared. So that's why I have a T right there. Now, this then becomes the summation from n equals 0 to infinity of T to the n over n factorial, the summation of T equals 0 to infinity of 2n T to the n factorial, and of course 0 here, and the summation of n equals 0 to infinity of T to the n over n factorial. Now we know from our calculus 2 that the summation of n equals 0 to infinity of t to the n over n factorial is equivalent to e to the t. And then we're going to look at the summation of, and I'm going to do that in blue. I'm going to do the summation of n equals 0 to infinity of 2n t to the n over n factorial. We want to see how we can make this a little bit simpler. Now, if I readjust this so that I can pull out a 2 and I pull out a t, then this can become n equals 0 to infinity. Rather, that's going to be 1 to infinity. N equals 1 to infinity. And then I'm going to end up with this adjustment. I'm going to have t minus 1 over n minus 1 factorial. And you're probably wondering, how did that happen? Well, remember that n factorial is the same thing as n multiplied by n minus 1 factorial. So I did that so that this n will cancel with this n. But I have to have equivalence. So when I put in n equals 0, that I will have the exact same thing as when I put in, I couldn't put in n equals 0 here because I wouldn't have the equivalence here. So I had to adjust for the index. Now, if that n cancels, I want to have this denominator match this exponent, or I want this exponent to match this denominator before I do the factorial. So if I factor out a t, which is not dependent on n, then I'd have a t out front, and then of course I would have started with n minus 1. Then the next adjustment I'm going to do is say, hey, let m equal n minus 1. If that happens, then this summation becomes 2t, the summation of m equals 0 to infinity, of t to the m over m factorial, which we know happens to be e to the t. So with all of that said, then I'm going to come over here. This matrix then becomes e to the t, 2t e to the t, 0, and e to the t. The matrix that is equivalent to e to the at is called the fundamental matrix for the linear systems of differential equations. And x prime is going to be equal to a multiplied by the x. If we write this capital X and x prime in terms of their column vectors, we're going to get this. And the matrix product can be wrote as a multiplied by a sub 1, a sub 2, a sub 3, the columns of that matrix. If the matrix X satisfies this equation, then we see that each column of the vector x sub I of the matrix X is a solution of the vector equation. So we have a new definition. A non-zero square matrix N is called the nilpotent if N sub k is the zero matrix for some integer where k is greater than 0. So in other words, what we're hoping for is, when we do our square matrix squared or cubed or to the 4th power multiplication, that we hope that it hopefully goes to 0. Here's some properties that we get. So if e raised to the 0 is equal, we have e raised to the 0, it should be equal to the identity matrix, which makes sense if we look at how we define e to the at, where 0 is a n by n 0 matrix and I is an n by n identity matrix. And then we know that this is easily seen from the series that how we define e to the at. If a and b commute, that is, and this hardly ever happens, if a times b is equal to b times a, then e raised to the a plus b will be e to the a, e to the b. The inverse of e to the at is e raised to the negative at, and the last property holds since e to the at multiplied by e to the negative at would be equal to e to the at minus at, which is e to the 0, which is I. Now, let's use the matrix exponential to solve this initial value problem. Now, if I go out to my calculator, a matrix calculator, and A, of course, is this matrix, A squared, I end up with 8, -4, 4, and 0. A cubed is going to be, well, let me erase this over here because I need this space. A cubed is going to be 20, -12, 12, -4. A to the fourth, because I'm trying to find patterns here, is going to be 48, -32, 32, and -16. Now, you can see that I'm going to have a hard time possibly finding a series that's going to satisfy this like I did with my first example. So rather than doing that, I'm going to bring in some information about our Calculus 2 and also some linear algebra. So the first thing, we have e to the a, not e to the at, but just e to the a, will be equal to the summation of n equals 0 to infinity of 1 over n factorial a to the n. Now this is our Calculus 2. Now what I'm going to write in blue is from linear algebra. If the matrix A and is a 2 by 2, so I should write that, a 2 by 2, has two distinct eigenvalues, lambda 1, lambda 2, with the appropriate eigenvectors, v1 and v2, then we're going to set the matrix P to equal the v1 in the first column and the v2 in the second column. We can diagonalize the matrix A to be P inverse multiplied by the matrix A multiplied by P, and I will get the diagonalization where I have lambda 1 in the first position, 0 in those other two positions, and lambda sub 2 in the 2, 2 position. So if that's true, then we know that A is going to be equal to multiplying both sides by P, and then I'm going to have the lambda 1, 0, 0, lambda 2, P inverse. And we also know that A is equal to P, lambda 1 to the n, 0, 0, lambda 2 to the n, P inverse. And you can check this yourself, or you can just look it up in any linear algebra book. So right now we're not going to prove it, it's going to be a given. And e to the a then is going to be equal to the summation of n equals, oh, that's a to the n equals 0 to infinity of 1 over n factorial a to the n. But this is a to the n, so this is going to be equal to the summation of n equals 0 to infinity of 1 over n factorial p lambda 1 to the n, 0, 0, lambda 2 to the n, P inverse. Because P and P inverse are not dependent on n, we can bring in the summation notation. So we have P, and we bring in the summation notation in my inner matrix. So it'll be the summation of n equals 0 to infinity of 1 over n factorial multiplied by n, lambda 1 to the n, and then 0 there, 0 here. The summation of n equals 0 to infinity of 1 over n factorial n sub 2 to the n, P inverse. Now, we know that this is just a real number, and in particular, what that real number happens to be is P, and then inside this matrix, I'm going to get e to the lambda 1, 0, 0, e to the lambda 2, multiplied by P inverse. So, all of this just to say that if the lambdas are distinct and we're working with a 2 by 2 matrix, we can go right from finding our lambdas, our eigenvalues, and our eigenvectors, and we can find our A that way. That just makes it so much nicer. So take note of that. Now, what happens when I don't have repeating, or when I have repeating eigenvalues, or I have complex? Well, we'll get to those too. Now, so let's talk about when lambda 1 is equal to lambda 2. Then I'm going to end up with, I'm just going to give this to you, P inverse of A multiplied by P is going to be equal to my lambda, 1, 0, and lambda. So from there, I can do my solving. And then we end up with A, and you can go through, just like we did up above, by doing the A to the N. It'll end up becoming A is equal to P, E to your lambda, E to the lambda, 0, E to the lambda, and then P inverse. Now let's look at our last case in which my lambda 1 and 2 is going to be complex. It's going to have some form where it's going to be A plus BI. Then I'm going to have distinct eigenvalues and distinct eigenvectors. That should be plus and minus. Then my P inverse of A, P is going to have the form of looking like this, A plus BI and 0 for the first row, and 0, A minus BI in the second row. In this case, A will then equal P, A plus BI 0, 0, A minus BI, P to the inverse, where I'm going to end up with A is equal to, this will be P, E to the A plus BI 0, 0, E to the A minus BI, and then P inverse. P inverse. Now, what happens, because we started out with this. We started out with E raised to the TA or AT. And you're thinking, how is that gonna change all of this? Well, the way it's gonna change all of this is up here when they're distinct. Right here, when they're distinct, we're gonna just add in this T. If they're not distinct, as in right here, then I'm going to leave this up to you to explore it if you're inclined. If you're not, that's okay too. That you're going to add in this T here, ooh, and that T there, and also this T here. So that's kind of nice. And you're thinking about, how does this affect this complex number? Well, it's nothing terribly surprising. A is going to be equal to P, and we're going to have E raised to the real part, which was the A part, A times T. So A of T. And then it's going to be your cosine of your beta part times T. And then plus the sine of beta T. And E to the AT is multiplied there. A 0 in this position, a 0 in this position, and this would be E raised to the AT, the real part, or the alpha, because what I've used in the past. And then it'll be the cosine of beta T minus I sine of beta T. So let's go ahead and do an example. So again, you're probably going to want to write these in your notes or not. I guess it just depends. You're like, man, I remember those. Cool. That's cool. Let's go ahead and go through an example here. Let's go way back over here. So the first thing we're going to do, of course, is find the characteristic polynomial, and I end up with lambda being 2. My eigenvector that is associated to that is going to be my V, which is going to be associated, is going to be 1, 1. My P matrix, I'm going to put in 1, 1, and then I just need a second vector that is going to be linear independent, so a good vector would be the 1, 0. And we know from what we just did that E to the AT is going to be equal to P. And then we have our matrix that goes here, which we know is going to be e to the 2t, because that's my lambda, te to the 2t, 0, and e to the 2t, multiplied by p inverse. All right, but I do need to find p inverse, so I'm going to go ahead and find that really fast with p inverse. It is 1 over the determinant, and this determinant is going to be -1, so this will be -1 multiplied by 0 and 1 switch positions. These switch signs, so my p inverse for this is nice. It is 1, 0, 1, 1, -1. So then my e raised to the at is going to be my P110, 1110, e to the 2t, te to the 2t, 0, e to the 2t, multiplied by 0, 1, 1, -1. And when I get totally done, I'm going to get my e to the at to be equal to e to the 2t plus te to the 2t minus te to the 2t, te to the 2t, and then my last position is e to the 2t minus te to the 2t. Now, as a quick check, we know this should be the identity matrix if t equals 0, and if I put t equals 0, this will go to 0, this will go to 0, this will go to 0, this term will go to 0, this will become 1, and this will become 1. So it's a really nice check. So then what I have is I have x, the matrix x has to be equal to e to the 2t plus te to the 2t minus te to the 2t, te to the 2t, e to the 2t, minus te to the 2t, multiplied by the 3 and 4. And then from there, I can get the general solution, replacing 3, 4 with C1, C2. And then that's it for that one. Let's take a look at this next example here. In this example, we find our characteristic polynomial, and we end up with a lambda of -1 plus or minus I. And so our eigenvector, one of them is going to be, of course, they're going to be complex conjugates. It's going to be, I am not going to leave fractions, so I'm going to have this as being 5, and this is 3 minus I. And then the other one, I'm going to call this V1. My other one, I'm going to get V2, which will be, this should be 5 and then 3 plus I. So then my P is going to be, actually I want to use my P is going to be 5, 3 minus I, 5, 3 plus I. Now on this, my middle matrix, when we do e to the p, e to the at, this will be p, which we have here. We still need to find the p inverse. I'll let you do that. And then this matrix, as we know, will be the real part. So e to the real part, which is -1t. And then it'll be the cosine of beta, which was 1, so just t, minus the sine of t. And then we have 0 in this position, 0 in this position, e to the -t, cosine of t, because my beta is 1, plus the sine of t, because my beta is 1, multiplied by p inverse. And I'll let you do the multiplication. I'll just give you the final answer. The final answer is e to the -t. I have the cosine of t plus 3, the sine of t in that first 1, 1, the -5, the sine of t. I have 2, the sine of t, and then in the last 2 position will be the cosine of t minus 3, the sine of t. And that's it for that example. Now let's take a look at this system where I've got x prime is equal to 5, -8, 2, and -3. And I'm going to find my lambdas with my characteristic polynomial, and when I do that, I get 1, which is repeating, just like we started out with before. My eigenvalue, or my eigenvector that's associated to this is going to be, so my v is going to be 2, 1. So a good choice for p would be 2, 1, and then 1, 0. Of course, I would find p inverse, which is -1 multiplied by 0, 2, -1, -1. Multiply this through. I'm going to get 0, 1, 1, and -2. So then my e to the at is going to be 2, 1, 1, 0 multiplied by, now my matrix here that I'm going to use, remember, is e to my lambda, which is 1t. And then it's going to be te to the lambda, which is 1t, 0. And then e to the lambda, which is 1t, multiplied by my inverse, which is 1, 0, 1, 1, -2. And I'll leave it up to you to go through the multiplication. I'm just going to give you the answer. So I have e to the t plus 4e to the t, 4t e to the t, 4t e to the t, minus 8t e to the t, 2t e to the t, e to the t minus 4t e to the t. All right, so then my x is going to be equal to, and since I don't have an initial value, this is just going to be that matrix again, e to the t plus 4t e to the t, -8t e to the t, e to the t, that should be 2t e to the t, then e to the t minus 4t e to the t, and then multiplied by, since I don't have the initial value, just c sub 1, c sub 2. And this is my final answer. Now, we can use a matrix exponential to solve a non-homogeneous system. And the way that we solve a non-homogeneous system, it'll be x of t is equal to e raised to the at. We're going to integrate from 0 to t of e raised to the negative at of s, b of s ds, plus e to the at of c, which is the same thing as from 0 to 2, e to the a t minus s times b, matrix b, s ds, plus e to the at plus the vector c. So as before, you're going to be so surprised. I need to find my lambdas, and I'm going to end up with a lambda sub 1 here. Lambda sub 1. Here we go, lambda sub 1, which is going to give me 1/2, and the eigenvector that is associated to that is 3 and 1. I'm going to have lambda, I'm going to call that v1. Lambda sub 2, I ended up getting 3, and the eigenvector that's associated to that was the -1 and 2. Now, I'm going to solve this slightly different. I'm going to use something called the fundamental matrix. And the reason I'm going to do that is because if I rewrite this here as x of t is equal to the fundamental matrix t, and I'll explain what that is in a minute. The fundamental matrix evaluated at 0 inverse x of the matrix x evaluated at 0 plus the integration from 0 to t of the fundamental matrix t, the fundamental matrix evaluated at s inverse f of s ds. Okay, so the fundamental matrix M, so M of t, is going to be equal to my e, and this is because I have distinct lambdas, e raised to the lambda 1 its eigenvector that's associated to it. And then we have e raised to the lambda 2 and its eigenvector that's associated to that. That gives me 3e to the t divided by 2 and negative e raised to the 3t e raised to the t divided by 2 and 2e raised to the 3t. So then my fundamental matrix evaluated at 0 would be 3, -1, 1, and 2. So then I would just have to find that inverse. So the m evaluated at 0 inverse would be equal to 6 minus, so it's 1/8, 2, 3, 1, and -1 in those positions. So we've got that. And then we need to find out what m of s is going to be equal to. Well, m of s is just evaluating that fundamental matrix at s. So we have 3e to the s divided by 2, -e to the 3s. And then down here, I'm going to have e to the s divided by 2, and I'm going to have 2e to the s 3s. All right. The other thing that I need to do is find that inverse, and I also need to identify what f of s is. Well, f of s is this. So that f of s is going to be, with the t being replaced with s, e to the 2s, and then e to the negative s. All right, so using this alternated version, I have x of t is going to be equal to my m of t, which is 3e to the t divided by 2, negative e raised to the 3t, e to the t divided by 2, 2e raised to the 3t, multiplied by my inverse, which is 1/8, 2, 1, -1, and 3, multiplied by my x naught, which is that, so it'd be 4 and -1, plus the integration from 0 to t of 3e to the t divided by 2 minus negative e raised to the 3t, e to the t divided by 2, 2e to the 3t, multiplied by the inverse of 3e to the s divided by 2, minus e to the 3s, or negative e to the 3s. I want to keep saying minus, but it's just negative. E to the s divided by 2, and then 2e to the 3s. This gets multiplied by e to the 2s, and then e to the negative s, ds. So I am going to find this inverse. This should be an inverse right there. So I need to find m of s inverse. So m of s inverse, this is going to be the determinant, so it's going to be 6. I'm going to add those exponents, so it'll be e raised to the 3.5, which is 7 halves, minus, and then I'm going to have, and this should be 1 over. I'm going to have negative becomes plus e to the, again, 3 halves, so 7 halves of s. And then these switch positions, so it's 2e to the 3s This becomes negative e to the s divided by 2. This becomes a positive e to the 3s, and this becomes 3e to the s divided by 2. So you can see that this becomes 7. It'll be 7e to the 14 over 2, so 7. So this will be 1/7 e raised to, it'll be 14 over 2, which is 7. It'll be negative 7s. And of course, I would just multiply that in there and then combine up everything there. Now, when I do the integration, this piece is not dependent on s, because this is in respect to ds. So that matrix is not dependent on the s at all. So that can actually be factored out. And then I would multiply these two together, those matrices together, and then I would integrate it component by component. So A11, A12, A21, A22. And so what I'm going to end up with, I'm going to just kind of jump to almost the answer. When I multiply all of these through, I'm going to get 3e to the t divided by 2, e to the 3t. I'm going to have e to the t divided by 2, negative 2e to the 3t. Well, it should be a plus, and then that actually is a minus. So that's my first matrix, and then my second matrix, which is by the integration and the multiplication. I'm going to get 3/7 e raised to the 2t minus 5 over 28 e raised to the negative t minus 2 over 7 e to the t divided by 2 plus 1 over 28 e raised to the 3t. In the second position, I'm going to get 10 over 21 e to the 2t minus 13 over 42 e raised to the negative t minus 2 over 21 e raised to the t divided by 2, and lastly 1 over 14 e raised to the 3t. Now I have basically these two vectors adding component to component. This is my answer. 3 over 7 e to the 2t minus 5 over 28 e raised to the negative t plus 19 over 7 e raised to the t divided by 2, and then 29 divided by 28 e raised to the 3t. That's the first position. The second position is 10 divided by 21 e raised to the 2t minus 13 divided by 42 e raised to the negative t plus 19 over 21 e raised to the t divided by 2, and then lastly negative or minus, and that should be a plus there, minus 29 over 14 e raised to the 3t. And holy smokes, that is my answer. That's it for this video.